So we're going to look now at what I mean by reactive intermediates. We're going then to look in particular at carbenes and quite a bit about N-Heterocyclic Carbenes, which have achieved a lot of prominence in recent years through what's known as organocatalysis. Then the following lecture will deal with benzynes and other arynes. So that's where you have a triple bond, if you like, in a benzene or related ring. And then the third lecture of this series will look at some things about organic radicals, single electron species. So this is for this afternoon, Introduction to Reactive Intermediates, Carbene Generation and Reactivity, N-Heterocyclic Carbenes in Organocatalysis. So what do I mean by a reactive intermediate? Well, this is just any reaction taken at random. This might be the free energy profile, free energy reaction coordinate. You have energy maxima, which are transition states. You have energy minima, which are intermediates, and then obviously you have products over here eventually. This intermediate is in quite a deep well, so it's potentially stable, might even be able to be isolated, because it's quite a big barrier either to it going forwards or going backwards. This intermediate is in a shallow well and would be therefore unstable, more likely to be a reactive intermediate, and because the transition state to products is not far above the energy of that intermediate. So most of unlike pericyclic reactions, most chemical reactions have fairly complex multi-step mechanisms and may have several intermediates, and as long as the rate of a reactive intermediate needs the rate of getting away from the reactive intermediate to be faster than the rate of forming the reactive intermediate. If that wasn't the case, then the intermediate could be regarded as fairly stable, maybe even isolated, if K2 is either similar to K1 or smaller than K1. So we're looking at things that come in shallow wells and are easy to move on to products over low energy barriers. So summarizing what I've just said in text, so a deep energy well, the first intermediate there will be relatively stable, may be stable under normal conditions, but under conditions of the reaction is converted into products. Shallow well, energy difference between the transition states to go backwards and forwards is quite small, so that will be an unstable intermediate, unlikely to be isolated, short lifetime, very reactive. So the reactive intermediates I'm talking about will have unique reactivities that allow access to other products you couldn't get in other ways. And just to remember that transition states at the maxima of the profiles are not discrete molecular species, could not be isolated even theoretically, because as soon as you touch them, their energy goes down one way or the other. But they can possess discrete geometry and charge distribution. Well, we saw that even in the 3,3 sigmatropic rearrangements in the session this morning. They are the highest point in an energy profile, whereas intermediates are minima. They determine rates of reaction. Here are some fairly reactive species and their nomenclature. In very, very extremely strong, unusual superacid conditions, you can even get 5-coordinate carbon, so you can get real carbonium ions. When I grew up, 3-coordinate carbon was called a carbonium ion. Traditionally, that should be a carbenium ion. So the onium ion should be one where you're 1 over the normal valency. Quite rare for carbon, very special circumstances. We're all familiar with ammonium ions or oxonium ions. Of course, we've got the neutral 4, 3, and 2 coordinate species for carbon, nitrogen, and oxygen. They're not reactive intermediates, that's just, in a sense, our baseline. We've got carbanions, amide anions, alkoxide anions are negatively charged species, so still 4 coordinate, but one of the coordinations is a non-bonded pair with, so that effectively a minus charge is a bond with no atom on the end of it. Now, somebody asked me before lunch what was LDA, lithium diisopropyl amide, and that's 2 isopropyl groups for the R group and an N minus with a lithium counterion as a very strong base. So if you weren't familiar with that, LDA falls into this family. It's a strong base. If you've got single, and this will deal with this tomorrow, if you've got single electron species, you've got carbonyl, aminyl, or alkoxyl radicals. If you've got electron deficient species, so 6 electrons, 3 coordinate, 1 below the normal valency, you've got carbenium ions, or carbocations, nitrenium, oxenium ions. And at the bottom here, this is what we're going to look at this afternoon, particularly carbenes. Nitrines exist, are formed in, as reactive intermediates in some processes. Oxenes, rarer, but nitrines we won't talk about. I'm going to talk about carbenes this afternoon. So that's the sort of nomenclature of all of these. Tomorrow I'm going to discuss arynes. Now this doesn't come out very well. That's supposed to be a triple bond. It just didn't project very well. I don't know why. There are other reactive intermediates I'm not going to deal with. Radical anions, where 1 electron is added to a neutral molecule, or radical cations, where 1 electron is removed from a neutral molecule. I'm not going to talk about those this week, but they do exist and they are intermediates in some mechanisms, but are not going to feature in these lectures. So let's look at carbenes. These are neutral, no charge. They're divalent or 2 coordinate carbon, highly reactive, and they have 2 non-bonded electrons. So divalent, 2 non-bonded electrons. These are 6 electron species around carbon. 4 electrons in 2 covalent bonds and 2 non-bonded electrons. They are generated in situ, cannot be isolated at room temperature, but special examples have been trapped in frozen argon below 77 K, so very cold, structure investigated that way. But that's an unusual situation. Those are quite dilute, so basically these species then are fixed in a frozen inert gas, so they can't react with each other or anything else. But that's a very specialized situation. So in terms of the using them in any synthesis, they are generated in situ in the reaction you're doing. What's their structure? They're considered to be sp2 hybridized. That means that the 2 covalent bonds to carbon and a 3rd orbital, which contain 1 or 2 electrons, are in a plane, and then there is another orbital available perpendicular to that plane. There are 2 electrons from the carbon that are involved in the 2 covalent bonds, sp2, pairing with whatever the attached atoms are. Then there are 2 non-bonding electrons, that potentially could have parallel or anti-parallel spins. So it could be paired or not. Wish my computer wouldn't do that. This leads to the possibility of having singlet carbenes or triplet carbenes. So what we mean by singlet and triplet, the spin quantum number of an electron can have two possible values, which are called plus and minus a half. But the big thing is two values. So the spin multiplicity, singlet or triplet or whatever, is the number of possible orientations of that total spin. So a singlet carbene would have the two non-bonded electrons will be anti-parallel to each other. They will be paired, and there's only one way of doing that arrangement. So the spin multiplicity is 1. It is a singlet. There's only one way of pairing up two electrons with opposite spins. On the other hand, if you have the two non-bonded electrons in parallel spins, then there are 3 arrangements there. You can have both electrons with a spin quantum number of plus a half, both with minus a half, or one of each. So you've got, if you like, if you want to look at it in sort of these arrow terms, you've got 2 spins upwards, 2 spins downwards, or 1 up, 1 down. So there are 3 possible arrangements of the total spin. So the spin multiplicity is 3. What does that mean in conventional terms that we would think of as looking at the carbene? If it's a triplet carbene, the 2 electrons, if they're parallel, they can't be in the same orbital. So 2 electrons in that case would occupy different molecular orbitals, and that species would behave like a diradical, and actually can be observed by electron paramagnetic spectroscopy, EPR, which observes, records radicals. So a singlet has paired, and that would look like this. So we have sp2 carbon, 2 sp2 bonds to whatever the substituents may be, and an sp2 non-bonded or lone pair in the 3rd sp2 orbital. That leaves an empty p orbital, which is slightly higher in energy than the sp2 hybrids. So that's why that one's left empty. So that's a little bit like a carbocation, or it would be if there was a 3rd group around the carbon. The triplet, to have parallel spins of the electrons, they've got to then be in separate orbitals. That means there's 1 electron in, you can look at it as having 1 electron in the sp2 molecular orbital and 1 electron in the 2pz orbital. So that's why you can see this behaves like a diradical. So there might be differences in behavior.
Sorry to interrupt you, but the hybridization of triplet state is sp.
Sorry?
Triplet carbene have the hybridization sp. Not sp2.
No, it's sp2. 3. If it was sp, then the 2 groups. The 2 groups. Sorry?
I think that is a 19 sp hybridization. Not as carbene.
The nitrine, yeah, that's, yeah, okay, yeah, because you've got less electrons. Yeah. In this case, it is sp2. If it was sp, then the 2 groups attached to carbon would be linear, but they're not. It's bent. The angle isn't exactly 120 because you've not got 3 equivalent bonds or non-bonded pairs here, but nevertheless it is a bent species, not linear. We will see, could potentially see some differences in behavior between singlets and triplets because of this different way of looking at where the electrons are. So how do you make them? One way of doing it is by taking a diazoalkane and heating it up because of loss of nitrogen gas. I don't know why, but my software doesn't seem to draw triple bonds very well. But here is one resonance form of a diazoalkane. So that's got the two groups on carbon, and then the third bonding is to nitrogen. But you can draw an alternative resonance form which has negative charge on carbon and plus on the first nitrogen, and that illustrates how you would lose gaseous nitrogen to give a carbene. Now that sort of reaction is quite difficult to control. I mean, loss of nitrogen gas, which is very stable, means this is not that difficult to do. The problem is it's difficult to control because of what the carbenes produced under those conditions will do. It can be explosive even. So diazoalkanes, you tend not to heat them up except having taken special precautions for potential big exothermic reactions. You can, however, under more controlled conditions, use metal catalysts to give intermediates where the carbene is complex to a metal. So whether those are really carbenes is arguable. You can call them metallocarbenes, or you can call them carbenoids, which means they behave as if they're carbenes. So they have similar structures and behave similarly. In those cases, you will probably write a metal to carbon double bond. But you can sometimes make those behave in a more controlled way as if they were carbenes, but they're not free carbenes as I'm drawing there. There are some other specialist methods of making carbenes, which I'm not really going to go into. What reactivity will they have? One typical reactivity is cycloaddition onto carbon-carbon double bonds, which is a very useful synthetic method for making cyclopropanes. And the results here can be different if you use, depending on how you generate the carbene, what energy it has. Carbenes generated without too much energy will probably be singlets. So you've got effectively a non-bonded pair and an empty orbital. The two bonds that you've got to make a cyclopropane from an alkene plus a carbene are regarded as being formed at the same time. And the advantage of that is that you know what the geometry of your cyclopropane is going to be. If you start with a Z double bond, cis, as I've shown there, you will still get it in the product. And if it was started as E or trans, it would be the same. So even if the alkene was tetra-substituted, you retain the geometry, relative geometry of the substituents. So that ties in with the idea that it's all happening at once. There's no time, no chance of there ever being a single bond in the middle that can rotate and change the geometry that you started with. If you form the carbene with higher energy, so maybe you take a carbene precursor like a diazoalkane and generate the carbene by photolysis, for example, so put in quite a lot of energy at once, then you may, in some cases, get a triplet carbene, and the difference there is you may lose stereochemistry. Not always, but maybe. So the two bonds are then formed sequentially, and you can regard that as then having a diradical intermediate and potential loss of stereochemistry. And then because the triplet carbene is essentially a diradical, single electron, one in each of the two orbitals not used for bonding. So if one of those reacts with one end of the alkene, that creates a radical left behind on what used to be the carbene, and actually you can't really see it very well here, but another single electron, another radical at the other end of the alkene. Those can then pair up because they're so close. I know that radical coupling, pairing, is not normally happening in radical chemistry because radicals are not normally close to other radicals in your normal situations, and we'll see about that when I talk about radicals tomorrow. But in this case, they're so close, that snaps shut. But this intermediate diradical does have the opportunity to rotate around the bond that used to be the alkene but is now a single bond, and therefore you can lose stereochemistry. So I've drawn it starting cis here. You still get some cis product, but it may rotate, and then before closing to give you some trans product. So if you want to make a specific stereochemistry of cyclopropane by this route, you would normally do it. Try to use a method that generates a carbene in its singlet state. Another thing that carbenes do is they can insert into single bonds. They can insert between the C and the H of sigma bonds. The problem with that is you can't always predict which CH bonds are going to be reacted. Reactions are often complex. Sometimes you can get insertion into sigma and pi bonds at the same time. You can at least have a prediction of what the major product might be if you've got some CHs at tertiary centers. They are weaker CH bonds than secondary or primary bonds. So you may see a predominance of reaction at tertiary CH bonds. But sometimes that's only a preference rather than a selectivity. If the carbene is very reactive, for example, you just make methylene carbene, CH2, then that's quite energetic and the insertion is pretty non-selective. So I mention it because it can happen, but it may not be useful in targeted synthesis. So I've just put in one example where the generation of carbenes and sorry, I beg your pardon, that's insertion. The other possible reactivity is rearrangements, and here's one that you may have come across, the Wolff rearrangement of diazoketones to ketenes, which are then hydrolyzed. So here you have an alpha diazoketone. Now, that's not the resonance form you would normally draw. You'd normally draw C double bond N plus, N double bond N minus. But if you draw the form as I did for diazoalkanes a couple of slides ago with C minus N plus triple bond N, then you can see how that can lose nitrogen. Commonly that's a photolysis, that's done by photolysis, but it could be done by heating. You just need some energy. Via a very reactive and not around for very long carbene next door to a ketone, you can get a 1-2 shift of the group, the other side of the ketone, moving across to the carbene. That would leave electron deficiency on the carbonyl carbon. That is balanced out by sharing the carbene's lone pair. So this is carbene effectively behaving as an electrophile by having an empty orbital, and nucleophile as well by having a filled orbital. That produces the ketene here, and then conventionally those are worked up by adding water, and the water will add at the center carbon there to give a carboxylic acid. In the problems in the session before lunch, we had an isocyanate, which is NCO, and a nucleophile attack that at the center carbon. So it's just the same here. The nucleophile is water, so that will attack at the center carbon. And ultimately that will give you the carboxylic acid. And you note, of course, what's happened is you've got a carboxylic acid, and the group, one of the groups in the original ketone has moved across to be next door to the carboxylic acid. And that's all I want to say about carbenes, because aside from those two, the cyclopropanation and the Wolff rearrangement, not so much use of them in synthesis. But what I want to spend the rest of this afternoon's talk is to discuss N-Heterocyclic Carbenes, which have received a lot of prominence in recent years for the reactions that they can catalyze, as I'll show you a little bit later. So they're often just abbreviated N-Heterocyclic Carbene as NHCs. They are effectively diaminocarbenes. So the two groups on the carbon are both nitrogens. They are strong sigma donors in inorganic chemistry terms. They have reactivities similar to other classic 2-electron donors, like phosphines, amines, ether oxygens. So they are used to replace phosphine ligands in many organometallic reactions. But they are stronger sigma donors than phosphines. But we're not going to talk about them in terms of complex into metals. We're going to talk about them as acting as organic molecules. So this is the general structure. N-heterocyclic, without those are N's in a heterocycle. The simplest ones are 5 members. They may or may not have another double bond in, so they may or may not have come from aromatic heterocycles. They may come from reduced heterocycles. We have 2 nitrogens attached to a carbenoid carbon. The nitrogens have to be substituted. Why are they relatively stable? They were first discovered for different reasons, but found to be relatively stable. Well, here's a picture you can think of. They are singlet carbenes, so the empty p orbital, this sp2 carbon, the empty p orbital can be regarded as stabilized by overlap with the 2, by pi donation from the 2 adjacent nitrogen lone pairs. And stabilized, and the lone pair on the carbene stabilized by sigma electron withdrawal in the sigma bonds to the electronegative nitrogens. So it's a classic case of nitrogen being a lone pair donor and a sigma bond withdrawer of electrons. So the combination of pi donation and sigma withdrawal helps to stabilize these species. So we've got pi donation by the outer plane p orbitals from nitrogen, sigma withdrawal by the electronegative atoms, nitrogen. What that does is stabilize the singlet, this electron arrangement, relative to the triplet. So it increases the singlet-triplet gap. Stabilizes the singlet carbene over the more reactive triplet carbene. So that's why these are relatively stable. But these electronic factors are not enough to allow you to isolate free carbenes. If it was just like this, what you do need to isolate them is to have steric bulk on these 2 nitrogen substituents and possibly on the backbone as well. And then you stand a chance of isolating them, or they are certainly more stable and less chemical reactions are possible. So they're stable enough not to decompose, but still reactive enough to react as catalysts. So we might see how that's going to happen, but we need first of all to think how you make these things. They can be prepared on quite a large scale. The precursors of them are stable and don't compose in air. So here's one. If you want symmetrical nitrogen substitution, you might take this aldehyde, glyoxal, it's 1,2-dialdehyde, treat with two equivalents of a primary amine and formaldehyde. You'd get imines formed with the two carbonyl groups, and then reactions of the nitrogens of the imine with formaldehyde, and that will give you this cyclic, in this case, imidazolium salt. And that's going to be a precursor to the N-Heterocyclic Carbene. If you want different substitutions on the two nitrogens, you would take glyoxal again, you would take formaldehyde, methanal, and one molecule of, or one equivalent of primary amine. That would give you the N-substituted imidazoline heterocycle, but then you put on if you want a different R group, you would then use that to alkylate the nitrogen lone pair. You can do slightly differently. If you want a saturated system, you, instead of starting with a dicarbonyl compound, you would start with a diamine, and then all you need is the single carbon between the nitrogens, and you could use something at the oxidation level of a carboxylic acid, and it's quite convenient to do that with an orthoester. So that's triethyl orthoformate and a bit of acid catalyst. So all of these create amidinium salts. NCN is with an unsaturation is an amidine, and as part of a heterocycle. These are imidazolium salts, or imidazolinium salts, dihydroimidazolium salts. So those are the precursors of the carbenes. All you need to do then is remove a proton from the position between the nitrogens. There's one proton in each of these between the nitrogens, so you need to remove that. So you take your salt, whatever it may be, maybe does, maybe doesn't have that double bond there, maybe the two R groups are the same, maybe they're not, but you take that, you remove the proton at the center position. Now, of course, if I do that, the first resonance form you might draw has a minus on the center carbon there and a plus on an adjacent nitrogen. The N-Heterocyclic Carbene is a resonance form of that. And there's a range of bases you can use for that. So there is an ylide resonance form for the N-Heterocyclic Carbene. Now, though that's a sort of simple one ring case, a whole load of them have been made, and I've just put a handful on here. There's just 5 there to show you different ones that have been made. Some with that are chiral, with asymmetric groups on. Some are functionalized. You can immobilize them on resins, so they'll be polymer supported. You can make them water soluble by putting ionizable groups on. In this one, you're making a metal complex. So what are we going to use them for? And this goes back to discovery by Breslow a long time ago of the role of, not quite an N-heterocyclic carbene, but the role of thiazolium carbenes in catalysis. And this actually mimics the way that vitamin B1, thiamine, works via a thiazolium relative to an N-heterocyclic carbene. He postulated that a thiazolium salt like this could be protonated in the same way, and that then that plus minus species has a carbene resonance form. And the proposal for the mechanism here And the way that vitamin B1 works as well is that the carbene or anion, whichever way you like to look at it, can react with, in this case, benzaldehyde, form an adduct, which then shifts a proton. There's a proton that was on the aldehyde here, and puts it on the oxygen, so lose it from the carbon, which forms this enamine structure, puts the proton back on the oxygen, and you have what's been commonly called a Breslow intermediate, after the man who first suggested it. This then can react as a nucleophile at that carbon that was the aldehyde carbon, because it's now part of an enamine function. So the lone pair on the nitrogen can push out and make this double bond nucleophilic of what used to be a carbonyl electrophilic carbon. So in this case, react with another benzaldehyde to make this bond, joining two benzaldehydes together, with one benzaldehyde carbon having acted as a nucleophile through the Breslow intermediate, and one having reacted as an electrophile, its conventional reactivity. If you then take this O- here, which has been, so this adds to a new benzaldehyde, that would make an O- here, but then if you swap protons between the two oxygens, once you get a minus on this one that was in the Breslow intermediate, then that can come back in and kick out, to make a carbonyl, kick out the thiazolium ylide carbene, however you like to draw it, and then that can go round and round. So you can make benzoin from two molecules of benzaldehyde, and essentially what we've done is we've made the aldehyde carbon into a carbon anion, a carbon nucleophile, via the enamine reactivity of the Breslow intermediate. But the carbene goes into the process, comes out again, and can go round and round, so it's a catalyst. So N-Heterocyclic Carbenes can do just the same. So we replace the sulfur in the ring by a substituted nitrogen, and these are the reactivities we can get. The same reactivity as in the thiazolium thiamine case. We can make a Breslow type intermediate by adding to a carbonyl compound and then tautomerizing the H on the carbon putting it on that oxygen, and that behaves like an acyl anion. That's the reactivity that Breslow discovered effectively, but you can do more than that. If you form a Breslow type intermediate from an alpha-beta unsaturated carbonyl compound, then that can use the enamine reactivity now, and that's put some nucleophilic potential at the beta carbon to what used to be the carbonyl of the alpha-beta unsaturated. So we've now got nucleophilic reactivity out here, which is be here in the original material. So it's a homoenolate. It's one further along than the enolate carbon. So overall, the NHCs can mean that we can not only get enolate reactivity, we can get enolate reactivity or nucleophilic reactivity at the next one out. And then we have azolium enolates or acyl azoliums, where we can react alpha substituted a variety of species, take that one for example, with the, so for example an ester, with the NHC, make an acyl NHC, and then make an enolate of that, and that will give us reactivity, conventional enolate reactivity, but it's actually faster, it's more reactive than the standard enolate. So all of these reactivities have been used, and I want to show some examples of how they've been used. What does organocatalysis mean? Well, it's what it says. It's catalysis by organic molecules, no metals, said to be green chemistry. The purification doesn't involve getting rid of any metals. Handling doesn't involve getting rid of any metals. There won't be any toxicity from any metals. The air and moisture sensitivity is different. Cost at the moment, well, some metals you use in catalysis are expensive, but at the moment I wouldn't say that the NHCs are desperately cheap, but they could be potentially. But of course the people who are working on this sell this very hard as a green type of chemistry. So let's look at some examples. Now the benzoin condensation of two benzaldehydes together, this is what Breslow discovered the whole thing on thiazolium salts with. You can now, that's become much more sophisticated. So if you use an NHC, which would be this center here, once you treat it with a strong base, potassium tertiary butoxide, so that's your NHC or carbene center, with an asymmetric center in it, you can get good yields using the same mechanism via, but having an optically active center in here. So you can get up 80-something% yields, and you get 90% in enantiomeric excesses. This is just one example, there are others. And I'm not going to go through these because it's difficult to appreciate them, but you can draw transition states that show you, allow you to predict what's going to be the favored isomer. And basically what's happening here is you've got a big group on one side of the NHC, so that's actually meaning that reactions can't happen on the same side as this tertiary butyl group. And again, as I say, I put these transition states in not so that we can talk them through, because it's difficult to appreciate them in a picture like this, but just to show you can make models, build models of what is going to be allowed spatially and what's not. When I finish this set of lectures, we will give you the slides for these as well, so that all the references at the bottom and so on you have available. Here's the Stetter reaction, which is similar, but it means your acyl anion generated, or equivalent, generated by interaction with the NHC. Again, here's the NHC, or at least it will be when I deprotonate it with base here. And it's now adding in a conjugate fashion to this beta position of this highly electron deficient double bond. So, similar process. I'm not going through the whole sequence, but here are two double bonds which have strong electron withdrawing groups on one end, and the NHCs provide you with an equivalent of the acyl anion to make this bond here, or this bond here. So doing conjugate or Michael type additions by what is equivalent of an acyl anion from this aldehyde here. Now this particular version that was introduced by Rovis in the not so long ago, maybe 10 years ago, did actually need these very highly activated double bonds with two withdrawing groups to make them electrophilic enough at the beta positions here to react with the nucleophilic species generated from the NHC and this aldehyde. So there's still, I haven't found one that's a little more general than that, but there may be lurking out there in the last decade. I didn't find it though. Now those are two examples of the acyl anion reactivity. What about the homoenolate reactivity? So here is an N-Heterocyclic Carbene, not saying about where that's coming from. These are two mesytyl groups, that's 2,4,6 trimethylbenzene, So quite bulky benzene rings either side here. So that adds to this conjugated aldehyde to give the initial adduct, which then shifts what was the aldehyde proton, shifts to the, comes off, electrons shift in to the nitrogen, and then the proton returns on the oxygen. So you make the sort of Breslow intermediate equivalent, but now we've got this extra double bond here. So another resonance form of that, using the enamine reactivity from the nitrogens, is that there is nucleophilic potential at that homoenolate position. So that's at the beta position of what used to be the alpha-beta unsaturated aldehyde. If you then introduce a second different aldehyde, I've put another aromatic one in there, then an addition takes place using that reactivity. If you then allow the enol that has been produced there to form back to the ketone, this structure has an error in it. There should still be an AR, another aromatic group on here, which is that aromatic group, that one, carried through to here. Then this alkoxide reacts with this carbonyl to kick out the NHC to go around the cycle again. And that closes a small ring, so the ARA's reappeared here. So there is an ARA missing there, I apologize. I only noticed that this morning, and I didn't have time to change it. So that's where we're forming a Breslow type intermediate from an alpha-beta unsaturated carbonyl compound gives you homoenolate reactivity. Now the same kind of catalytic cycle can be drawn in a number of cases, and Bodie has, now working in Switzerland, but an American guy, has shown that you can make do a whole number of different things there. You take an alpha-beta unsaturated aldehyde, this particular NHC, or it is when it has a base present, so when you deprotonate what I'll call the NHC position, you can make one of those homoenolate equivalent Breslow type intermediates, and depending on the electrophile, you can carry that through to a whole bunch of different products. Now, I don't propose to go through all of those cycles, but it's basically the same kind of cycle as on the previous slide. It's just that when you add the homoenolate to these different electrophiles, you get different reactivity possible to finish the cycle off. So I just put that in to show you the versatility of these homoenolate species, and I suspect by now that other variations are out there in the literature. This is just one paper, well, a series of papers actually. 1, 2, 3, 4, 5 papers there that explored these various options. I guess it was one option in each paper. I can't remember now. And if you look at these, we get good diastereomeric ratios, and we get good enantiomeric excesses. And the enantiomeric excesses have been created because these are optically active centers in the N-Heterocyclic Carbene, which means that one face of the Breslow type intermediate you generate is blocked because of this, this big chunky bit here. You are using, some people say about N-Heterocyclic Carbene organocatalysis that we are still using quite high catalyst loadings, whereas with some organometallic or metal catalysts you can go down quite low. But over the recent years, the loadings required have come down and down and down. So I suspect that this 10%, when these were published about 10 years ago, a little bit more, I suspect that you can probably get away with lower percentage catalyst loadings, because obviously the more catalyst you have present, the more you have to separate out when you isolate your products. So here's an Azolium enolate example. So where are we? There's the NHC. Add to it this is just an illustration. Add to a ketene. It would add at the center carbon of the ketene, which is the which is there, that dot, to give an Azolium enolate. That can then add to the this imine. So the Azolium enolate is a nucleophile at its furthest out position there. That can add to the imine and create this carbon-carbon bond. And then if you carry that on, this nitrogen can close onto the carbonyl there and kick out the NHC to go round again. So this is a way of making beta-lactams from ketenes. So this is the equivalent. So it's a 2+2, formally a 2+2 cycloaddition. It isn't really it's only a cycloaddition in its result. It's not a cycloaddition as a pericyclic reaction, because you form one bond and then you form the end carbonyl bond. So it's a 2+2 via an intermediate that then ring closes. But nevertheless, it is a way of overall adding the double bond of a ketene to the double bond of an imine in 2 steps and getting a beta-lactam out of it. This has been developed independently by a Chinese group and by a friend of mine in St Andrews University in the UK, Andy Smith. And if you want to, you can write the mechanism in more detail than that catalytic cycle. The catalytic cycle is just to illustrate that you get the N-Heterocyclic Carbene back again out of this. Right. Okay, so those are examples of the 3 different kinds of reactivity I specified: the acyl anion, the homoenolate, and the azolium enolates. Of course, there are lots of examples of NHCs in organocatalysis, and I've just put in a handful, a half a dozen, as illustrations. Okay, so that's the end of what I want to say about carbenes and N-Heterocyclic Carbenes to introduce reactive intermediates in general. That's the final session for today. I think we kick off, I guess, at 10 o'clock tomorrow morning, when I'll continue with benzynes, and then followed with the second session tomorrow morning will be on radicals. Okay, that's it. I should say I'm going to stick around if anybody's got any questions about this or any of the earlier things.